The movement of giant planets like Neptune may have influenced the orbits of the icy bodies in the Kuiper Belt as they migrated outward from the Sun. This region has become a focal point for investigating clues about early solar system materials. The icy bodies in the Kuiper Belt are believed to be largely unchanged since the formation of the solar system, serving as time capsules that contain primitive materials. Analyzing these objects can reveal information about the early chemical environment of the solar system, including the presence of complex organic molecules that may have been precursors to life. Recent observations suggest that some Kuiper Belt objects, KBOs, contain not only simple ices but also complex organic compounds, adding an intriguing dimension to their study. The discovery of two significant dwarf planets in the Kuiper Belt, Haumea and Makemake, has further enriched our understanding of this region. Haumea, slightly smaller than Pluto but larger overall, was discovered in 2005 and has a highly inclined orbit. Its discovery prompted a redefinition of what constitutes a planet, sparking debate within the astronomical community. Makemake, with its elongated shape resulting from its rapid rotation, showcases the diverse structures and physical characteristics of Kuiper Belt objects. Recent findings have also revealed binary systems among KBOs, where two objects orbit a common center of mass. These systems provide insights into the formation and evolutionary processes of Kuiper Belt objects. For instance, the binary system of Pluto and its moon Charon, discovered in 1978, has yielded valuable data about their sizes, masses, and orbital characteristics. Similar discoveries in the Kuiper Belt, such as the binary configuration of Haumea and its moon Hyakka, further highlight the dynamic interactions within this distant region. The search for a hypothetical Planet 9, believed to be a large, unseen planet affecting the orbits of distant KBOs, continues to drive exploration and observational efforts. If Planet 9 exists, it could represent a remnant from the early solar system or a more recent addition. The gravitational effects of such a planet could provide insights into the processes that have shaped the outer limits of the solar system. Ongoing observations involve astronomers employing various techniques to identify this elusive planet, including deep sky surveys and advanced computer models to predict its location and characteristics. The exploration of the Kuiper Belt also includes international collaboration, with missions organized by various space agencies and research institutions. NASA's New Horizons mission, which provided the first close-up images of Pluto and its moons, has set the stage for future explorations of the Kuiper Belt. Upcoming missions proposed by the European Space Agency and other international partners aim to further investigate this remote region, potentially sending spacecraft to study additional KBOs and gather more detailed information about their composition and behavior. Moreover, the study of the Kuiper Belt extends beyond our solar system, as similar structures known as debris disks have been observed around other stars, offering insights into how planetary systems develop. By examining these distant systems, astronomers can gain a better understanding of the formation of planetary belts and the potential for habitable conditions around other stars. This comparative approach helps contextualize our knowledge of the Kuiper Belt within a broader framework of celestial and planetary evolution. The ongoing research into the Kuiper Belt is not only about uncovering the secrets of our solar system but also about understanding the larger processes that govern planetary formation and evolution. Insights gained from studying this remote region can inform our knowledge of other planetary systems and contribute to the search for extraterrestrial life. As technology advances and observational techniques improve, the mysteries of the Kuiper Belt will continue to unfold, revealing new aspects of our celestial neighborhood and the fundamental processes that shape it. Overall, the Kuiper Belt represents a treasure trove of scientific opportunities, offering crucial insights into the early solar system and the dynamics of planetary development. The ongoing investigation of this distant region, driven by advanced telescopes and space missions, promises to yield exciting discoveries and enhance our understanding of the outer solar system. As researchers delve deeper into the enigmas of the Kuiper Belt, we are on the brink of uncovering remarkable new knowledge about our place in the universe. The Kuiper Belt is regarded as a chilly region filled with countless comets and minor planets, and astronomers have only recently begun to unravel its hidden mysteries. In fact, the existence of this vast ring of icy objects was only confirmed in 1992. There is even speculation that a large, entirely unknown planet could be lurking out there, possibly influencing the Kuiper Belt's dynamics. Recently, the James Webb Space Telescope focused its attention on this distant area and made an exciting discovery. Some of the celestial bodies in the Kuiper Belt might actually emit heat, and potentially even harbor life. For a long time, the outer reaches of our solar system remained largely unexplored, with vast areas remaining blank on star maps. Previously, we only knew that the origins of comets were thought to lie dormant in this far-off region, stretching far beyond Neptune's orbit. The nature of the movements within the Kuiper Belt and the existence of its celestial bodies were mysteries for many years. One of the first to address the mystery of the origin of comets was Jan Hendrik Oort in 1950. The Dutch astronomer proposed a model based on a spherical region at the farthest edges of the solar system, serving as a natural reservoir for comet nuclei. He theorized that when this cloud was disturbed by the gravity of interstellar gas clouds or nearby stars, some fragments would be ejected from their orbits and become periodic comets. While this theory explained the orbits of long-period comets, it could not account for the characteristics of short-period comets like Halley's Comet. This limitation led astronomer Gerard Kuiper to conclude in 1951 that there must be a second comet reservoir closer to the Sun. He suggested it would appear as a vast ring of icy debris just beyond the orbits of Neptune and Pluto. Kuiper's theory provided a possible explanation for the challenges faced by Oort's model, but it remained unproven for decades due to the lack of telescopes capable of detecting smaller celestial objects at such great distances. It wasn't until 1992 that Kuiper's hypotheses were confirmed, thanks to the efforts of astronomers Jane Liu and David Jewett at the Mauna Kea Observatory in Hawaii. After 5 years of searching, they successfully identified the first trans-Neptunian object in the Kuiper Belt, the faintly glowing spot 15,760 Albion. Today, we know that the Kuiper Belt extends approximately 30 to 50 astronomical units beyond Neptune's orbit. An astronomical unit is the average distance between the Earth and the Sun, roughly 150 million kilometers. The Kuiper Belt is believed to gradually merge with the inner edge of the Oort cloud, making this cold repository about 10 times larger than the asteroid belt between Mars and Jupiter and potentially 3 times more massive. So, what does the environment in the Kuiper Belt actually look like? Scientists estimate that there are over 70,000 objects larger than 100 kilometers in diameter within this region, but smaller bodies are nearly impossible to detect, even with powerful space telescopes like Hubble, due to the immense distances involved. It wasn't until 2019 that a team of researchers succeeded in identifying a Kuiper Belt object measuring less than 10 kilometers across. This 1.6-kilometer bump provided evidence that smaller bodies also exist in this remote area. However, we are still far from understanding the true number of objects in the Kuiper Belt. What we do know is that it is home to several dwarf planets, which ultimately led to Pluto's reclassification as a dwarf planet. As more Plutoids, objects of similar size, were discovered in the Kuiper Belt, the International Astronomical Union decided to redefine the term planet in 2006. Since then, Pluto has been categorized as a dwarf planet, but who knows if another celestial body in the Kuiper Belt might soon join the ranks of recognized planets. In fact, there are growing signs that another unseen planetary world may be hiding in the outer reaches of our solar system. The first indications of the hypothetical Planet 9 were suggested in 2015 based on the orbits of 6 larger objects in the dispersed region of the Kuiper Belt. Researchers have found that some dwarf planets, such as Sedna, have eccentric, highly elliptical orbits with their major axes oriented in the same direction and are tilted about 30 degrees relative to the ecliptic, which is the plane of Earth's orbit around the Sun. Following this revelation, astronomers were able to identify additional Kuiper Belt objects with similar characteristics. But is this merely a coincidence? If Mike Brown from the California Institute of Technology is correct, the answer is a resounding no. According to his analysis, the probability of such similarities being coincidental is only 0.7%. Instead, the shared orbital patterns suggest the gravitational influence of one or more objects, possibly including Planet 9, affecting these celestial bodies. While one might initially suspect that Kuiper Belt objects exert influence over each other, Closer examination reveals that the area would need to contain an object significantly larger than previously thought. The expected elective methodology is based on the existence of a ring structure composed of numerous smaller fragments, whose combined gravity is responsible for the orbital anomalies observed in Sedna and other trans-Neptunian objects. This theory should also be examined in the context of a model, although the Kuiper Belt would need to contain significantly more objects than currently assumed. The third and most compelling explanation involves the gravitational influence of a previously unseen planet in the Kuiper Belt. According to the model, this hypothetical planet 9 would have a mass approximately 10 times that of Earth and a diameter slightly smaller than that of Neptune. It is believed to orbit at a distance of around 4,500 astronomical units, which means it is, on average, about 20 times farther from the Sun than Neptune. Its orbital period is estimated to take an astonishing 15,000 years to complete a single revolution. According to astronomer Mike Brown, the likelihood of Planet 9 existing is quite high, with estimates suggesting a probability of over 90%. However, despite this strong statistical backing, Planet 9 has yet to be confirmed as a real celestial body. This is puzzling considering that humanity has been observing the night sky for millennia, and historically, only 2 new planets have been identified in the solar system. The reason for Planet 9's absence from this list could be its current position in the far reaches of its orbit, rendering it virtually invisible to even the most powerful telescopes. Moreover, model estimates indicate that Planet 9 may emit an intrinsic glow as faint as 0.006, which is even lower than Neptune's value of 0.01. Additionally, the primary radiation from Planet 9 is expected to be predominantly in the infrared spectrum, resulting in a surface temperature of approximately 47 K, or minus 226 degrees Celsius, making it only about 35 degrees warmer than its cosmic surroundings. Under these conditions, Planet 9 would be best detected in the far infrared spectrum, but whether and when it will join the list of recognized planets remains uncertain, as it may only be a matter of time. Recent findings from the James Webb Telescope regarding the Kuiper Belt have implications not only for the search for hidden celestial bodies but also for the potential existence of extraterrestrial life. Initially, one might think of the Kuiper Belt as an inhospitable zone, filled with cold and lifeless objects due to the extreme conditions present there. The idea of liquid water or living organisms in such a frigid environment seemed almost impossible. However, new data collected by the James Webb Telescope challenges this notion. A study led by Christopher Glaine's team at the Southwest Research Institute focused on the dwarf planets Haumea and Makemake. During their research, the scientists discovered recently heated frozen methane, suggesting that these dwarf planets possess hot interiors capable of transporting fluids and gases to their surfaces. Furthermore, Glaine believes that the relatively young methane deposits imply that these dwarf planets could have subglacial oceans. This discovery mirrors the findings from moons like Europa, which has already demonstrated that many celestial bodies in the solar system harbor liquid water beneath their icy surfaces. If Glaine's hypotheses are confirmed, it would suggest that some of these frozen dwarf planet worlds offer conditions conducive to life. At this stage, however, such possibilities remain purely speculative. To validate these theories, a dedicated mission to explore these distant frontiers seems incredibly promising. After all, NASA's New Horizons mission to Pluto and beyond has already unveiled a complex world with diverse geological features, revealing that the Kuiper Belt is far more intriguing than previously thought. To put the fascinating data from the James Webb Telescope into context, Glaine hopes that NASA will soon send another spacecraft into the Kuiper Belt. According to him, we will likely be astonished by the wonders awaiting us there, allowing us to continually be surprised by the marvels of space. The Kuiper Belt, often compared to the asteroid belt but located much farther out, remains one of the least understood regions of our solar system. This vast ring-shaped area is populated by a diverse array of icy bodies, many of which are remnants from the early solar system. In addition to its significance in understanding the formation and evolution of planetary bodies, the Kuiper Belt also provides insights into the dynamic processes that shape the outer regions of our solar system. It serves not only as a reservoir of ancient ice but also as a window into the past, revealing the conditions that prevailed during the early stages of planetary formation. One of the most captivating aspects of the Kuiper Belt is its potential to uncover the origins of the solar system's architecture. The distribution and characteristics of Kuiper Belt objects, KBOs, offer valuable information about the gravitational influences that have shaped the solar system. For instance, the orbits of certain KBOs exhibit significant perturbations that suggest interactions with large bodies, potentially including those beyond our current observational reach. These gravitational relationships may have played a critical role in shaping the solar system as we know it.